Good morning, friend. As you know, I am taking the course which is Aircraft Stability and Control. Today I am in lecture number 23, which is Hinge Moment and Hinge Moment derivatives. As you know, my name is Dr. Dwivedi, professor from IIR Hyderabad. Today's my topics which I am going to cover are stick force, then hinge moment, then horn balance and mass balance. And what we are going to answer in today's lecture is what is stick force and hinge moment, need of horn balance, need of mass balancing of control. These things we are going to answer in today's lecture. So I'm going to start with stick force. Till now we have not discussed about any force which is experienced by the pilot. We are only concerned with stick fixed condition where a constant angle of attack of the control surfaces are fixed. They are not floating. In the previous class, I have discussed about the floating also. And today, I am going to discuss about the stick forces and how these forces are applicable. So, stick force applied by the pilot to deflect elevator control to particular angle is called the stick force. Means this is the force which is applied by the pilot. If you see in the cockpit, pilot is holding the stick. Okay, that is called the control stick. So in the control stick, how much forces are, this is the, is sitting here, and how much forces are applied by the pilot, then we say that the stick force is applied. Okay, that is the meaning of stick forces. And this stick force, we have two types of controls. First is the reversible control and another is irreversible control. So what do you mean by the reversible control? Okay, this we will be discussing in the next slide. And irreversible control means, reversible means when the pilot is applying and changing the stick direction, your control surfaces are also moving. And when you move the control surfaces from the outside, the stick will also move. It is vice versa. If pilot is moving the stick, the control surfaces, elevator, aileron and rudder will move. And once you move these surfaces, elevator, aileron or the rudder, stick will also move. So this type of control is called the reversible control. But nowadays we use some electrical and some electronics fly-by-wire. So it is not happening. So in the previous or olden days, we used to have reversible control. Here, if you see this diagram, here this one is your stick. This portion from here to here is a control stick, and pilot is sitting here. He is the pilot. So if it is pulling like this, it is called pull. It is called the negative. Just you can see here. So pull means if he is pulling towards, if it is like this and I am pulling like this, it is a pull. And if elevator, in this pull, elevator goes up. This you can see here that in this diagram. And for the push, whenever I am making this control away from me, it is a push. And if it is the push, elevator goes down and it is called the positive elevator deflection. Okay. So in this diagram, you can see that for the pulling, if you pull this rod, then what will happen? By the pulling, this will move in this direction and this will move in this direction. So this, your elevator will move upwards like this. Okay. So for the pulling, if you pull, it will go like this. Okay. And your elevator will go up. And so up is called the negative. Okay. And once you push away from you, that is a push. It is called the positive. So once you push it, then what will happen? The elevator will go down. The elevator position will be like this. Okay. So this is the down condition and this is the up condition. So you can see that the pulling means elevator making up. Pushing means elevator making down. Okay. Then what will happen? Okay. So cruising. If you want to cruise at CL trim, so we want to reduce the speed. Okay. So if you want to reduce the speed, so pull the stick. So we have to pull the stick. If you want to reduce the speed, so you have to pull the stick in such a way that lift is equal to weight. So it is in the trim condition. It is called the CL trim. So CL to increase elevator has to go up, as elevator is not fixed but to float. So for this condition, we have to pull down and your elevator will go up. Okay. So to make a trim condition, we have to pull, and by the pulling, elevator will go upward. Okay. So now just I am going to discuss about the hinge moment. So what is the hinge moment and how these things are applicable? So we know that the hinge moment is a function of alpha t and delta E. So what is alpha t? Alpha t is the angle of attack at horizontal tail, and delta E is a deflection of elevator. Okay, so for the plus alpha t, if the alpha t is plus, just you can see here in this diagram, this is your tail from here to here. This is the tail. Okay, this is the tail and this is the elevator here. Okay, this is the elevator. So if it is a plus alpha t, then what will happen? This plus alpha t will make here positive angle of attack in the elevator also, and elevator will go up. Elevator will go up means float up. It is not done by the pilot. It is by the aerodynamic forces which are generating in the tail side or tail plane and elevator, and this elevator will try to go up due to the aerodynamic forces. These aerodynamic forces will generate a pressure distribution like this, and a net force will be going upward. Okay, so this net force, it is called the L here or LH. This is by the this is the delta L, and here it will call CH. CH is a hinge moment coefficient. Okay, and this hinge moment coefficient will be negative, means in the anti-clockwise direction. So we have to make this, when HM we have to make 0, means there is no hinge moment. It means that angle is called the floating angle. So means it is floating in such a way that there is no hinge moment. So this CH will be countered by another CH, then it is called the hinge moment is 0. So here we have the typical variation of hinge moment. You can see here hinge moment HM versus here delta E when alpha is equal to 0. So here this you can see this case 1 I have mentioned here. Here alpha is equal to 0 means the flow is going like this straight way on this, but delta E we have made the positive delta E. So delta E1, delta E, you can see here 1, 2, 3, 4, 5. So delta E1, delta E2, delta 3, delta. If you plot like this, we will get the curve like this, but we have to consider only the linear part of from here to here. So this from here to here is a linear part. As you increase the delta E, elevator deflection, once we increase the delta E, HM will also increase. Okay, so and this will happen when we consider as a linear case, and alpha means the this angle of attack of the flow is 0, but deflection delta E is experienced. So here this we can see that this HM is varying with alpha t, but first case we have taken that alpha is 0, only delta E is varying. In the second case here, if you see here, delta E is 0. Here delta E is 0 means that deflection of elevator is 0 and alpha is varying. So you can see here alpha 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and so on. And if in this condition delta E will remain 0, so what will happen? This will also give a, as you increase this alpha T, your HM will also decrease. Okay, HM is decreasing. So this you can see here that, so what we have to do in this, you can see that delta E, so it is increasing here, and this HM is negative. Okay, and here also this nose down, here also this HM is negative. Okay, so we have to find out the HM. So we can see that when alpha is 0 and delta E is positive, that is the case 1, the HM will be negative. Okay, so dHm by d alpha, d delta E is less than 0. So this is for the case 1. Okay, so this is the here case 1. So we can see that dH means it is a hinge moment. The variation in the hinge moment and with the variation of elevator deflection, if you see, it will come the negative. If it is coming the negative, then it is a stable case. For the case 2, when elevator deflection delta E is 0, but we are changing the positive angle of attack, HM will be negative. So here again, dH by d alpha is less than 0 or negative. Okay, as shown in the above plot 1 and 2 respectively. So here we are assuming that variation of HM versus alpha and variation of hinge moment versus delta E are linear. So here I have shown in this area only linear zone only I am going to take this issue. Okay, so this you can see that it is now I am going ahead with some example. I am giving alpha T as a 5 degree and alpha and delta E, the deflection of elevator, as 5 degree. So here we can see that in this case HM alpha 5 at delta E is equal to 0 plus HM at delta E is equal to 5 degree and alpha is equal to 0. Okay, this you can see here. So it is one, we have to take the one vary and another will remain 0. Here delta E is equal to 0. Here alpha is equal to 0. This is the beauty of linear T assumption. Okay, so here, so delta HM is equal to, what will be here? Delta HM by d alpha into d alpha plus del HM by d delta E into delta E. So HM is equal to, here again the same. So here the coefficient of hinge moment, that is the CH. H is a hinge moment, and if you take the coefficient, we have to divide this equation by half rho v square SECE. Okay, so here if you see here, this CH will be here CH alpha T into alpha T plus CH delta E into delta E. Here we are taking CH is equal to 0, then floating of the elevator can be found. So if you make this CH is equal to 0, here we have put CH is equal to 0, then CH alpha T into alpha T plus CH delta E into delta E float, because this will now, this delta E will become float. So float means there is a pilot is not applying any force. It is just moving and it will remain there, but no force will be applied. So now we can find out delta E float is equal to minus CH alpha T divided by CH delta E into alpha T. Okay, so here we can see that value is negative. This delta E float, the value is negative, so it will float up. We have given the first that if the value of elevator is coming negative, it shows that it is going up. So it will float up. Elevator goes upwards. Okay. So here we can see that CH alpha T here is negative. CH delta E is also negative. So net delta E float deflection will be negative. Okay, in this case, if the CH alpha T is negative, CH delta E is negative, then delta E float will be negative. It means it will float upwards. This is the tail and this is the elevator. In this condition, it is floating upward. This you can see here. Okay. So when CH alpha T is 0, okay, when this CH alpha T is 0, then what will happen? If this CH alpha T is 0, then what will happen? So when CP and hinge line, are in the same point, then there will no hinge moment. Okay. So elevator will not float. So if hinge line HL and is equal to CP, both are in the same point. Just I will explain here what is the meaning. This is the tail, this is the elevator, and this is the hinge line HL, and this is the CP. If this CP and this are in the one point here, then CH alpha T will be 0. So in this case, there will not be floating. Okay. So this is the issue, and that we have to take care, and we should make sure that CH, this L and this thing, it should be, both should be in the same point. Okay. Now we have to see that we have made that this delta E, we have find out. Now how these things are balanced. We have seen that this in floating condition, if this this delta E float here, this is the float, is equal to minus CH alpha T divided by CH delta E into alpha. So differentiating with respect to alpha, if we differentiate this equation with respect to alpha, then we will get d delta E float by d alpha is equal to minus CH alpha T by CH delta E. This shows what rate of elevator will float. This shows the rate of float of the elevator. Here CH alpha T is equal to 0. The upper, this numerator term CH alpha T is equal to 0. If it is 0 means no hinge moment. So when alpha is equal to 0, this is not done by the pilot, but done by a design known as a horn balance. So how this thing CH alpha T will be 0? This is not by the pilot is not going to apply some force so that the moment will not be 0. To make the moment CH alpha 0, we have to have some design of this aircraft in the control, and that part which we designed to make this thing CH alpha T 0 is called the horn balance. Okay, so horn balance is a device which makes this hinge moment 0. So if we make the hinge moment 0, it means that pilot need not to apply it can leave the hand and your stick will be there on the particular position and pilot will feel less tired. Okay, that is why the horns are used in all the control system, and I am going to discuss next in this. So what are the horn balance? This you can see here. Here is your tail part of the aircraft fuselage. This is the tail of fuselage. Here you have fixed your horizontal tail. This is the horizontal tail. It is shown here, and here you have the elevator. This is the elevator here. So, and here this part is increased. Okay, this part is part of the elevator. So when elevator is going down, this part will go up. So above the hinge line and below the hinge line. So hinge line is here. This is the hinge line. So this part is elevator and this part is horn. This part here I have shown here. This is the horn, and this horn is ahead of the elevator hinge line. Okay, so what is happening here? For alpha T, the elevator nose upwards. Okay, for the positive, if the elevator is going down, its nose will go upward. Okay, the leading edge will go upward. So this leading edge when go upward, the horn will also go upward. However, elevator will generate force upward and the moment of hinge will be anti-clockwise and moment of the hinge for horn will be clockwise. So the hinge moment is balanced by the horn. So pilot need not to apply the force on control stick continuously. Okay, so here this you can see here I have shown here the aerodynamic forces generated by the elevator. When you deflect down, F2 will be generated by the elevator, and here it is F1 will be generated by the horn. So this F1 into X1, just you can see here F1 into X1, this force, these moments are generated by the horn, and F2 by the elevator, F2 into X2. So F2 into X2 is generated by the elevator. So if F1 X1 is equal to F2 X2, there will be no moment. No moment, and so HM will be 0. So pilot need not to apply any force, and he has to leave in the new position the stick, and it will remain there without applying any force. So horn is ahead, so it is HL to the hinge line. The moment generated by elevator is neutralized, so the CH alpha T reduces by the horn. So here by this case CH alpha T will be 0. So horn is making CH alpha T 0. That is the purpose of the horn. The purpose of horn is that pilot should not apply any force after deflecting the any control. Okay, so that is the purpose of this horn. Okay, now we can go ahead further. We know that we have discussed a lot about this delta E. Elevator deflection required is equal to delta E is equal to delta E naught plus d delta E by d CL trim into CL trim. This is the stick fixed case. Now, because here stick is now floating, so delta E float. What will be the delta E float? So delta E float is equal to delta E naught plus d delta E by d CL trim into CL trim. We know that this delta E float we have already calculated. It is minus CH alpha T by CH delta E into alpha T. We will put this value here and then we will calculate it. So stick force Fs or neutral stable is Fs is equal to 0. So if Fs is equal to 0 means no force is applied by the pilot. Okay, so if delta E float here, this quantity is less than delta E naught plus delta E d delta E by d CL trim is less than, the pilot has to pull the stick. Pilot has to, you just see, if this delta E float is less than this delta E naught plus d delta E by d CL, so he has to pull the stick. He has to pull means elevator has to go upward. And if this delta E float is greater than d E naught plus d delta E d CL trim, the pilot has to apply the push force on the stick, and that time elevator has to go down. Okay, but if Fs is equal to 0 means if delta E float is equal to delta E plus d delta E by d CL trim is equal, then there will not be force. If delta E float is less than the delta E plus d delta E by d CL trim, then it is a pull force, and if it is greater than, the float is greater than this, then it will be the push force. So we can understand that there is a force applied by the pilot if both the delta E float is not equal to the delta E naught plus d delta E by d CL trim. Here I have shown some diagram for the horn balance of aircraft control. You can see here horn for a elevator, horn for this you can see horn balance, and you can see here that this is the elevator, this is the elevator here, and this elevator is, this is here horn, this part is called the horn. Here also if you can see this red part is here, this red from here to here, this is the elevator, and this white part, this is called the horn. Okay, so if it is going down, you can see here, if you are making this thing down, it will generate a force like this upward, and here this, and here is the hinge line, so this F2 and this is called X2, and here also it will generate a force in this direction, this is the F1, and from here to here is X1, so this F1 into X1 is equal to F2 X2, so delta E float will be 0, no pilot force is required, Fs will be 0. Okay, so in this way we can, that is the use of horn, and in this way the this moment, the hinge moments are balanced by the this horn balance. And this is also in the rudder also, if you see this is the rudder, and here also this is called the horn. This, so if you move left it will go right, and if you move right it will move the left. So it is also making that rudder float, that is called delta R float. This makes Fs 0 for the rudder control. Rudder pedals we have, rudder pedals, pilot need not to apply, pilot need not to apply any force for directional control. Okay, so that is the purpose of this this system. Okay, so I think it is very much clear now what is the use of this system. So now next topic is mass balancing. Okay, why we have to do some mass balancing in aircraft controls? It is very much essential. Okay, so mass balancing, flutter occurs when the control surface is displaced from its intended deflection. Because the ailerons are on the long narrow wings which can twist under load. They are the surface most prone to oscillate. If the center of gravity is behind the hinge, the surface can move like a pendulum and undergo force in simple harmonic motion with increasing amplitude. Aiding balancing weight, which makes the center of gravity and hinge line coincidence solves the problem. These weights may be in the nose of the surface or lighter masses attached further ahead of the hinge externally. What is the meaning of this mass balancing? You know, there is a hinge line. I have discussed just now that this is the your horizontal tail and this is the elevator, and here is the hinge line. I am just HL, and the CG of this elevator, this is the elevator, and the CG of this thing, this is the CG. If the CG is behind, then what will happen? There will be, due to deflection of this elevator, it will try to oscillate. So what we have to do? We have to add some weight here at the nose of this elevator, so that the CG, the HL will be equal to CG. Both are coinciding, and the CG will lie on the top of the hinge line, and there will not be any moment. So this flutter will be avoided, and this your control will be balanced. So it is very much essential that time to time during the aircraft maintenance, we have to see that aircraft controls are balanced. Okay, so balancing is very important for this. You can see here how this mass balancing is done. Okay, so this you can see here. Here is the one, this is the mass. This mass is added in this way. This is the elevator here. This is the elevator, and here one this part is hanging, and some mass as per the required we are putting this mass, and this mass makes that this hinge line and the HL is equal to CG. This is the mass balancing. Here you can see, and here also you can see small mass is here, small mass is here. These masses are purposely it is make at the nose of this. If you see like this elevator here, we are fixing a mass here like this. It is hanging like this. Okay, so it will give the mass balancing. So control responses and mass balancing. Mass balancing is designed to prevent flutter on control surfaces. So the flutter means what? It is vibrating like this, like this. So to avoid that thing, we have to do the mass balancing, because if it is fluttering, your failure of the control will be very frequent. So to avoid that, we have to do the mass balancing. So flutter is a vibration of the control surfaces which is often experienced at high speed. It is caused by pressure distribution over the control surfaces and can be particularly bad if the control surface center of gravity is not in the line with the hinge point. So if CG is not in the line of hinge point, this flutter is likely to occur. To avoid flutter, we can employ mass balancing to align the center of gravity closer to the hinge line. So that is the purpose of the hinge line. Okay, so this you can see here that in this diagram that it is a moving surface. You can say elevator. It can be used in aileron and elevator and the rudder anywhere. So here the CG is here. So if you hang like this from here, then it will be shifting from here to in this line. Okay, that is the purpose of this hanging the mass. So in this way we can do the mass balancing of the aircraft. Okay, so I have completed this class. In next class I am going to take these topics, that is the revision of stick fixed and stick free expressions, derivation of stick force Fs, stick force gradient dFs by dV, then force to trim the airplane, and hinge moment coefficient. These points I am going to discuss in my next class. Please be tuned and watch my next video. It will be really interesting. Okay, so I think this this lecture is also very good because it gives about the mass balancing, it gives about the horn balancing, and it is very important parameters for any of the engineers of aeronautical or aerospace stream. Okay, thank you very much for this joining my class. These are the references I am taking from these books. Okay, thank you very much for joining my class. Okay,
like, share and subscribe. Hit the bell icon for more updates.